Hello. In this video, I'm going to show you how to use polynomial long division to integrate a rational expression. First step is to figure out when to use it, and I figured that out by looking at the degree of the two polynomials in my rational expression. The degree of the denominator here is going to be 2 because the highest power of the polynomial down here is 2. And on the top, the degree is going to be 3 because that leading term has a power of 3 on it. So this makes this an improper fraction. Whenever the degree of the numerator is greater than or equal to the degree of the denominator, I have an improper fraction. And if we look at an example with numbers that would be similar, would be something like 21/2. The numerator is bigger, so this is an improper fraction. And to turn this into a mixed number, what I would do is some long division. So I'd take the numerator, put it inside the long division, and the denominator on the outside, and then divide. And I start by focusing on the leading terms, the leading number inside. So 2 goes into this 2 here. How many times? Well, the answer is 1. And then I multiply these two values and subtract that product down below. So 1 times 2 is 2, so I subtract 2 down below. I get 0 from subtracting that, and then bring down the 1. And then I ask myself again, 2 goes into 1 how many times? Well, it goes in there 0 times. I get a 0 here, and I am now left with a remainder of 1. And so to deal with that remainder, if I wanted a mixed number for an answer here, I take the 1 and divide it by the divisor. So I get 10 1/2 as my mixed number. We're going to do the exact same thing with our polynomials, only it's a little more complicated because we have variables in there. So let's start with that setup. The 25x squared plus 4 goes on the outside. Negative 75x cubed minus 25x squared minus 8x minus 3 goes inside. And again, I focus on the leading term. Here I'm going to focus on both leading terms. And I ask myself, what do I have to multiply 25x squared by to get negative 75x cubed? And the answer here is I have to multiply this by negative 3x. So up top, negative 3x, and then I'm going to distribute that negative 3x to the terms of my divisor and subtract it down below. So negative 3x times 25x gives me negative 75x cubed, and then negative 3x times 4 will give me a negative 12x, and I'm going to line that up with the x term, the other polynomial. And just like with the numbers, I'm subtracting this, so the whole thing should have a negative out front that distributes to both terms. Okay, so now I'm going to subtract. So negative 75x cubed minus negative 75x cubed, that gives me 0. The negative 25x squared can just be dropped down. Negative 8x minus negative 12x is plus 4x, and then minus 3 drops down. And now I repeat the process. So 25x squared times what will give me negative 25x squared? Well, the answer is negative 1. And so I'm going to, again, distribute the negative 1 to the divisor and subtract it down below. So negative 25x squared minus 4. And subtract that. Leading terms cancel again. 4x can be dropped straight down. And negative 3 minus negative 4 is plus 1. At this point, when I compare my leading terms, the 4x has a lower degree than the 25x squared. So this means I've got my remainder. This is my remainder, and I am done with the long division. And I will do the same thing here that I did with the numbers. I had a remainder of 1, and so I divided it by 2. Here it will be plus 4x plus 1 divided by 25x squared. Okay, so we've got Our long division done. Now dealing with a proper fraction here because 4x has a lower degree than 25x squared. And I can get back to the integration part of this problem. So integrating, I can now split this up into the front part, the negative 3x minus 1 dx will be its own integral, and then plus the integral of 4x plus 1 over 25x. Yeah. So the first part I can just go ahead and integrate using power rule. So this will become negative 3/2 x squared minus x. For the second part, this one's kind of tricky, and I'm actually going to split this up again into two separate integrals, one for each term of the numerator. So I'll have a 4x over 25x squared plus 4 plus 1 dx over 25x squared plus 4. Believe it or not, both of these can be integrated using substitution. So with the first one, I'll do a u substitution where u is going to equal the whole denominator, 25x squared plus 4. And that would make du equal to 50x dx. Looking at my integral, well, I have an x in the numerator, so that's great. I don't have a 50, though. So I'm going to actually divide the 50 over to the left side here. So 1/50th du is going to be equal to x dx. So the x dx gets swapped out for 1/50 du in this example. So if I start rewriting this, row out front. The 4 I'm going to bring out front and add in the 50 to that, the 1/50th. And then do my u substitution. And this is actually going to be du over u when I get there. And so that's just going to be the natural log when I integrate that in the next step. Let's go ahead and do a substitution for the second one as well while we're at it, though. This one is a little different. Whenever I see an x squared plus a number in the denominator and a constant on top, I want to think of the in a table of integrals integral. This is pretty much the only one I allow in this class, and it's very useful. This one comes up a lot. So the formula, it's one worth memorizing. If I have, say, dx over x squared plus a squared, then that will integrate to 1 over a tangent inverse of x over a plus c. And so that's what I'm going to do here. I do have a 25 out in front of that x squared, though, that makes things a little more difficult. So I will be doing a u substitution on this as well. Now, I already used u, so I'm going to use a different letter. Let's use w. And I'm just going to take what's being squared here. So this can be rewritten as 5x squared, like that. And so the w is going to be the 5x, which means that dw is 5x. And since I don't have a 5 hanging around for this substitution, I'll divide that over to the left. So 1/50th dw is going to equal dx. So that's my swap for the dx in the substitution. Okay, so back over here, I'm going to have a 1/5 throw out front, dw over w squared plus 4. And now that matches the formula perfectly for tangent inverse, and so that's what I'll do to integrate this. So rewriting again, I get negative 3/2 x squared minus x plus 4 over 50, and the integral of 1 over u is the natural log of the absolute value of u, plus 1/5. And now I'm going to use the formula. So a here is 2. That's 2 squared gives me the 4. So this is going to be a 1/2 tangent inverse of w over 2. And then we've finally integrated everything, so I can throw the plus c out front. Only thing left to do now is to reverse the substitutions that I did, and I'll have my final answer. So negative 3/2 x squared minus x plus 4 over 50 which, oh, I can reduce that. Let's go ahead and reduce that to 2 over 25. Natural log. And u was 25x squared plus 4, which is always going to be positive. So I really don't need an absolute value anymore. I can just do parentheses. Not wrong to leave the absolute value in there, but it's not necessary either. Plus 1/10 tangent inverse. And w was 5x, so this is 5x plus c. And so it was a lot of work, a lot of algebra I have to remember on top of the integration, but I was able to integrate this using long division. And I didn't even have to bother with a partial fraction decomposition at any point here. And really the reason for that was this denominator here was not factorable. It was an irreducible quadratic there, and so I had to come up with another method other than partial fraction decomposition to get this one done. But we did get an answer.